Welcome back to the Robot series. In today's episode, we are diving into the brains behind modern electronic and robotic systems, the microcontroller and the microprocessor. These two components form the intelligence center of almost every technological device we use today. While they may sound similar, they serve very different purposes in the field of electronics, robotics, and artificial intelligence. A microcontroller is a small computer built on a single integrated circuit that contains a processor core, memory, and programmable input and output peripherals. It is designed to perform specific control tasks such as reading sensors, controlling motors, displaying messages, or managing automation processes. Unlike a microprocessor that needs several external components to operate, a microcontroller comes with everything built in, making it the ideal choice for embedded systems and robotics projects. Microcontrollers are used where real-time control is required because they can respond almost instantly to changes in sensor readings and user inputs. One of the most popular families of microcontrollers is the Arduino series. The Arduino Uno, for instance, operates at 5 volts and uses the 8MB328P chip running at a speed of 16 MHz. It comes with 14 digital input and output pins, 6 of which can be used for pulse width modulation, 6 analog input pins, and built-in communication interfaces like UART, SPI, and I2C. The Uno is perfect for beginners building LED systems, robotic vehicles, or sensor-based automation. Closely related to it is the Arduino Nano, which uses the same 8MB328P chip but in a smaller form factor. It also operates at 5 volts and offers 14 digital pins and 8 analog inputs. Because of its compact size, the Nano is ideal for projects with space constraints, such as mini-robots or wearable devices for larger and more complex systems. The Arduino Mega 2560 provides a powerful solution. It operates at 5 volts and runs on the 8MB2560 processor with a 16 MHz clock speed. It provides 54 digital input and output pins, 16 analog inputs for UARTs, and a large 256 kilobytes of flash memory. This board is ideal for advanced robotics, automation systems, or any project that involves multiple sensors and actuators. The Arduino Leonardo is another model powered by the 8MB32U4, which operates at 5 volts and features 20 digital input and output pins and 12 analog inputs. What makes the Leonardo special is its ability to communicate with a computer directly through USB, allowing it to act as a keyboard or mouse, perfect for human-machine interface projects. Another impressive model is the Arduino Micro, a miniature version of the Leonardo that also uses the 8MB32U4 chip. It operates at 5 volts and supports serial, SPI, and I2C communication, making it perfect for embedded robotics and portable systems. Moving a step higher in processing power, we have the Arduino Duo, based on the Atmel-SAM 3X8E ARM Cortex-M3 processor. It runs at 84 MHz and operates at 3.3 volts, providing 54 digital input and output pins, 12 analog inputs, and 4 UART communication ports. This board is perfect for real-time control, high-speed data processing, and precision robotics applications. The Arduino Pro Mini is another lightweight microcontroller that uses the 8MB328P chip. It can run at either 3.3 volts or 5 volts, depending on the version, and uses an 8 or 16 MHz clock. It has 14 digital pins and 6 analog inputs but does not include a USB port, making it lightweight and suitable for battery-powered devices. Finally, the Arduino MKR1000 combines a microcontroller with wireless communication capabilities. It uses an ARM Cortex-M0 processor that runs at 48 MHz and operates at 3.3 volts. It has 13 digital pins and 8 analog inputs, with built-in Wi-Fi connectivity, making it perfect for Internet of Things projects that require wireless data transfer or cloud-based control. Now that we understand microcontrollers, let's move to microprocessors. A microprocessor is the central processing unit, or CPU, of a computer system. Unlike microcontrollers, microprocessors do not include memory or input-output peripherals on the same chip. They rely on external memory modules such as RAM and ROM, as well as external interfaces and storage systems. This makes them suitable for more complex computing tasks, where high processing power, multitasking, and large data handling are required. Microprocessors are used in personal computers, smartphones, tablets, and advanced robotic systems that depend on artificial intelligence, image processing, and large-scale computation. One of the most widely known microprocessors is the Intel Core i7, which is found in many modern laptops and desktop computers. It operates at speeds ranging from about 2.5 to 5.0 GHz, supports multiple cores and threads, and includes integrated graphics. It typically operates between 1.2 and 1.5 volts and connects to the motherboard through an LGA socket. With the ability to handle billions of instructions per second, it is ideal for heavy computation, AI simulation, and design software. The AMD Ryzen 7 is another popular microprocessor featuring 8 cores and 16 threads, running at speeds between 3.6 and 4.5 GHz. It uses the AM4 socket and provides excellent multitasking performance for applications like 3D modeling, CAD systems, and robotic simulation for embedded and low-power applications. The Intel Atom processor is a strong option. It operates between 1.4 and 2.4 GHz, consumes very little power, and typically runs on about 1 volt. It's ideal for portable devices, IoT systems, and industrial control computers. When it comes to compact computers designed for learning and experimentation, the Raspberry Pi series stands out. The Raspberry Pi 4 uses the Broadcom BCM2711 microprocessor, which is a quad-core ARM Cortex-A72 running at 1.5 GHz and operating at 3.3 volts. It comes with 4 USB ports, 2 micro HDMI ports, Gigabit Ethernet, Bluetooth 5.0, Wi-Fi, and a 40-pin general-purpose input/output header. It supports operating systems such as Raspberry Pi OS, Ubuntu, and Windows IoT Core. Because of its versatility and affordability, it is used worldwide for robotics, IoT gateways, home automation, and AI-based experiments. Another member of the same family is the Raspberry Pi Pico, which is based on the RP2040 dual-core ARM Cortex-M0 Plus processor, running at 133 MHz. It operates at 3.3 volts and provides 26 GPIO pins, 2 UARTs, 2 SPI buses, 2 I2C interfaces, and 16 pulse width modulation channels. The Pico is perfect for projects that combine the simplicity of a microcontroller with the power of a small processor. Another popular single-board computer is the BeagleBone Black, built around the Texas Instruments AM3358 ARM Cortex-A8 processor, running at 1 GHz and operating at 3.3 volts. It provides 65 GPIO pins, Ethernet, USB, HDMI, and serial interfaces. It is used in industrial automation, robotics, and educational systems that require precise real-time processing. For artificial intelligence and machine learning, the NVIDIA Jetson Nano is a game-changer. It uses a quad-core ARM Cortex-A57 processor with a 128-core NVIDIA Maxwell GPU for parallel processing. It operates at 5 volts and provides USB 3.0, HDMI, Ethernet, and GPIO interfaces. It supports platforms such as TensorFlow, PyTorch, and CUDA, making it ideal for AI-based vision systems, autonomous robots, and voice recognition. Another compact but powerful computer is the Intel NUC, or Next Unit of Computing. It is a mini PC that uses Intel Core or Atom processors and supports HDMI, USB 3.0, Ethernet, and Wi-Fi connections. It operates on 5 to 19 volts DC and is often used as a control hub for home automation, server systems, and compact robotics control stations. Technically, the major difference between microcontrollers and microprocessors is that microcontrollers combine the CPU, memory, and input-output interfaces on a single chip, making them perfect for embedded applications where the system needs to control sensors and actuators directly. They typically operate between 3.3 and 5 volts and handle one application at a time. Microprocessors, however, focus on complex computation and require external memory, storage, and peripheral interfaces. They often run on higher voltages and execute multiple tasks simultaneously, usually under an operating system like Linux or Windows. In conclusion, microcontrollers and microprocessors each serve vital roles in the modern world of electronics and robotics. Microcontrollers are designed for precision control, direct hardware communication, and automation, the heartbeat of embedded systems. Microprocessors, on the other hand, are designed for intelligence, multitasking, and computation, the brain of advanced computing and AI. Understanding both gives you the foundation to design smart systems that can think, act, and evolve, from simple robots to powerful AI-driven machines.